Okay, here we go. Okay, it's turned for the presentation. So today we're going to discuss this paper called MAGMARS, a melting model for the Martian Mantle and the FeO-Rich peridotite. So it's a paper mainly based on modeling, based on the thermodynamic modeling using MATLAB, which they call the MAGMARS. So simulating the melting the Martian basalt source conditions. And the first author is Max Collinet, and currently he's a postdoc at German Aerospace Center. I think his advisor is Doris Brewer, the very last author, who is an experimentalist, and she's she's senior. But Tim Grove, which was Max Collinet's PhD advisor, according to the information I could find online, is more senior. So, and Tim Grove is also a member of National Academy of Sciences of the States. So for Max, he started his life in Belgium, and then moved to MIT, and then moved back to Europe. So for a lot of high temperature experimentalists, they normally also pay attention to the meteorites. And for him, that he focused quite a lot on the planetary science for Mars and the Moon. So here I would like to show a little bit about the composition, the bulk silicated composition of the Earth, Mars, and the Moon, so far as we know. For the Earth, people get it from the basalts as well as the peridotite samples, so that we can calculate the bulk silicated composition of the Earth. That's more well known. But for the Mars and the Moon, which lacking the peridotite, we gather composition either from the basalts, and then you calculate what their source composition should be. And another way is that people get the meteorites from the Mars and Moon that collected on Earth at Antarctica or Tibet, somewhere. And then people look at those meteorite composition considering the core mantle fractionation, and then you could get a bulk silicated Mars or bulk silicated. So that's a different way so that people could get their compositions. So if you look at their compositions, we could compare their silicon dioxide composition is very similar. For the titanium, the Moon could be richer. But of course, there are variations in every person's estimate of the compositions. But we can see some general difference between these different models. And for the Moon, the aluminum oxide concentration is not fixed. There are different models. Some people propose the Moon is aluminum rich. Some people propose aluminum poor on the Moon. So that's uncertain. But for the iron content is more certain for the Earth. It's about 8 or 9% for FeO total. And for the Moon is similar because people think that according to current evidence, mainly based on the giant impacts hypothesis, the Moon was formed by a giant impact from the Earth after the Earth was formed. So of course, the Moon should have a somewhat similar composition with the Earth's bulk silicate composition. Not exactly the same, yeah, but probably losing a lot of volatiles. So similar in terms of FeO content, but Mars has much higher FeO content. It's not a fixed number. People have the estimate from 14% all the way to 20% of FeO on Mars. But according to the InSight mission, where people put a seismometer on Mars, now the FeO content is estimated closer to a lower bound of Mars, likely closer to 14%. But still, Mars is more iron-rich than the bulk silicate Earth and the bulk silicate Moon. And since Mars is more FeO-rich, of course, Mars will be MgO poor compared to the Earth and Moon, as expected. For calcium, somewhat similar. Nickel and chromium, there are a lot of uncertainties. People don't know so much. For alkali contents, that's not so well known. And for water content, people know a little about the Earth that the H2O is in the order of 100 ppm. I mean, not exactly, people have different opinions, but it's something like that. But for Moon, people think that's very dry. So 1 ppm or this level. Mars is somewhere lying between the Earth and the Moon. We don't know the exact number. It's still being debated. So, as we can see, back to this, people know the Earth fairly well. So for the Earth's bauxite composition, there are less controversies, but for the Mars and the Moon, there are more controversies. So people are still trying to figure it out. And for this paper, so what they are collecting, what they're trying to address are the Andiron-Dak class basalt, which are considered to be primary basalts, that the melting product from the Martian mantle. And their composition could be analyzed by this in situ, what they call it, the miniature thermal emission spectrometer. So basically, this is a thermal infrared remote sensing instrument carried by the rover Spirit and Opportunity. So that's some of the recent, that's a relatively recent ones. And then the more recent ones, like Curiosity. So that's some of the missions. And the early missions was called the Vikings on Mars in 1997 or 1995. So people could have ways to understand what's going on and have some understanding of the basalt composition of the Mars. Of course, you cannot analyze the trace elements here. So that's unknown. But even so, people are still debating about that, about the bauxite composition of the Mars or the mantle source composition. So that's still unknown. So for this work, they are trying to address this through the forward modeling, is that they trying to figure out what are the source composition of the anti-rock basalt source. So first, they perform several experiments in at a not so high pressure, considered to be the basalt source pressures, and then with the varying phosphorus concentrations. So it's some more data that contributed to the community. And then they combine all this experiments data together. In particular, they want to emphasize a lot of experiments that are FeO-Rich, which are the Martian peridotite composition so far as we could know. And then they provide updated thermal barometer. And so that's how normally a lot of experimental petrologists do, is that you can control the temperature and the pressure, and they know the composition. Of course, you can say, okay, this is a thermal barometer. In the real world, you only have the compositions in the field, but you could use what people created in the laboratory and to try to figure out their temperature. And then they go on to answer the question, what is the source composition of the Martian basalt by using the primitive or depleted mantle, and then trying to look at different melting conditions to see what are their end results. And then they try to compare with the Andiron-Dak basalt to say which one is the likely one. So the experimental approach, I'm still an experimental petrologist, so I know what they're doing. So they have two series of experiments. One way is more straightforward. So you put the composition, then you put the temperature, pressure, and then you melt the rock samples, then you analyze the melt composition and the other mineral composition. So this is one way to do it. But there are always a lot of tricky parts for every method that's being used. So one tricky part here is that when you only have very small amount of melt concentration, for example, 5% melt and 95% solid, system experiments, then it's very hard to measure those 5% melt. And maybe those 5% melt are not in equilibrium with the rest of the samples. So there's also danger for that. So one way experimentalists are doing that is that you do the reverse experiment, where you do put the melt composition and the solid composition together. Then you put these two compositions together to do the experiment. And what you are expecting is that, for example, you may start with 30% melt and 70% solid. And then as the reaction goes on, reaching equilibrium, the melt will shrink from 30% to 5%. And then with equilibrium with 95% of solid. And through this method, the melt could be more likely to keep their original composition. because they started from the melt composition and then looking at the cooling result. So this is just some of the tricks, and people Cuba trying to do this because the second series experiments can confirm the first series experiments if they agree. That means the system should have reached equilibrium. So as we learned in the thermodynamics tells us the final result. But to achieve the final status, you will have different ways of achieving that. And maybe you will never reach the final status due to the inequilibrium. For example, not enough higher temperature, it takes a very long time to reach equilibrium, or physically, the melt are separated from the rest samples. So people are doing this to confirm the thermodynamics. So that's why they're doing that. So these are the experiments that are showing here. As you can see, the melt are just concentrated in a pool, a very small pool here. So you can see that the melt proportion is very small. And you can also see that there are some melts, for example, in figure B, that are lying really far away from a lot of other parts of the samples. So those melt, maybe they will not reach equilibrium. So people have doubts about that. And so that's why people do the reverse experiments or the second series experiments here. And then they move on to the next stage, is that they try to model a given composition in the source and what's its likely outcome product of the basalt. And so, but the given composition, which is just a guess. People guess about depleted peridotite, guess about the primitive peridotite of the Mars, which nobody collect any of the peridotite samples on Mars. Just let you to remember. So there are three scenarios they are modeling here. One scenario called near fractional polybaric. Or NFP. So you can look at this. So fractional means, okay, fraction. 分离结晶的. So it just fractionate something out, the melt. And the polybaric means poly means many. Baric means pressure. The polybaric means multi-pressure. So you look at this, the zone here. So you zone from, maybe here they're trying to say from 3 GPa to 1 GPa. So it's zoning where they have it's a zone, it's like column that they produce melt. So this is the this one looks like a little bit more like a real situation that could be possible. And then for the batch melting, it's an easier phenomenon. So batch, you could interpret from the word that you are all one batch, right? You're all together in the room, so nobody leaves the room. It's a closed system equilibrium. So it's a closed system. You form the melt them never leave and interact with them. So it's one batch. Everything's in one batch. So it's called a batch equilibrium. And then the third one is called the near fractional isobaric. So that is isobaric. Iso means the same. Baric means pressure. So you constrain everything the same pressure, and once it generates a melt, those melt leave the system. That's called the fraction. So being apart from it. So it's open system. So once melt generated, they're gone. So they consider three situations, and here they look at the result. But we can look at the result later before we'll come back to look at the result. But let's first look at how they do the near fractional polybaric. Okay, this one is a little more complicated. Batch is easy because it's a one-time game. So for this one, I just copy paste them. It's a bit too long before I could summarize. I want to read them so that I could refresh my memory of knowing how it goes. So for near fractional polybaric melting, so it's melting in a zone. So the calculated composition with a small amount of melt, 0.1%. I just let you know, you will never reach 0.1 with a person in an experiment. Or it's very hard. It's very hard for us to see them unless you use other ways to do them experimentally. But in calculation, you could also do that because you use mass balance. Although mantle adiabat, so there's a mantle adiabat of the Martian pressure, temperature and progressively lower pressure. So they assume a melt generated, for example, at the 3 GPa, and then it goes to shallower pressure, maybe 1 GPa. So this column that they're assuming the melt is going to generate. So temperature of the solid is not predetermined. So it is calculated from composition of the first melt increment that would appear at any given pressure if the mantle of a specific chemical composition was melting. So by this, they say the solidus is not fixed. It is composition dependent. So the composition of the solidus is the composition that have already considering the melt going away. So 0.1% melt going away. So those 0.1% melt always carries incompatible elements. Of course, here they don't consider trace elements. So major ones like aluminum, for example, that they prefer going to the melt. So that's what they assume to start in their modeling. And then they go on to the process, whether melting has begun or not, the composition of the hypothetical 0.1 with the percent melt increment is calculated to determine the temperature of the effective solidus at the pressure of interest. So they say they always assume 0.1% melt before they calculate the solidus. So it's okay, although it's not perfectly right, because if there's no melting occur, of course you won't have 0.1% melt. But I think in this situation it's okay, because you look at the major elements, even you consider the 0.1 weight% melt, it won't affect the bulk composition too much. So this is a reasonable assumption and easy to do in the codes. And initially, this temperature is higher than the temperature of the mantle adiabat. So this assume a high temperature, but because solid temperature decreases faster than the temperature of the mantle adiabat with decreasing pressure. So they say the solid temperatures decrease faster than the temperature of mantle adiabat. So mantle adiabat doesn't decrease too much. For example, at 3 GPa, if we assume it's 1500 degrees C, and then when 1 GPa is probably like 1470 or something like that. So the slope is not too steep. But the solidus will decrease quite a lot for peridotite. So by 1 GPa, the solidus could depress by 100 degrees C or something like that. We're going back to see the figure later on. And then they say because and the mantle temperature eventually exceeds the effective solidus. That's true. That's how the Peridotite generated on the Earth too. And then once the melting begins, all the melt produced above a fixed critical melt fraction is progressively removed, and the bulk composition and mineral model melting residual are continually updated. Okay, they say this is fractional. So they say if a melt is generated, once it's generated more than 0.4 weight%, and then they put the melt away from the closed system in the residual. And then the temperature of the mantle is also decreased to account for the loss of latent heat. So they consider latent heat here. So they also adjust the open system. Because the open system considering here. And the solid temperature continually increases due to the decrease of incompatible element concentrations. Of course, the peridotite solid is always composition dependent. Finally, all melt increments produced along the adiabat are poured together in the crust. So of course, here they consider melt generated for many times. So each time you generate some melt, then you put those melt there. The next time you add some melt, once those melt going out of the system, then you add them there, then you accumulate that together. So this is something likely close to what is going on to a real situation. And then for the MAGMARS, when they calculate this for the thermodynamic equilibrium, basically they are trying to figure out the different thermodynamic equations, basically minimizing the Gibbs free energy. So they have a different way of doing this. And the different parameters they have been using, for example, CP, heat capacity. Actually, that's don't know how he's calculating for his melt heat capacity for his project. But people have different minerals, heat capacity, measured, etc. People do the interpolation here to solve those equations. So basically, this is an iterative process. So now let's go back to look at this. They have 3 different situations. In figure D, I think there's a neo-fractional polybaric melting. So here, the Martian basalt, here, okay, they're showing here. Here's NFP. That's a near fractional polybaric. So you consider zone. So you're doing that. They're just assuming that's what that solidus change. So the solid changing. No, sorry. That's the adiabat. I think that's adiabat. I think. And then the solidus is the dashed curves. I think they're trying to say that. And the magma solidus is slightly different but similar, still similar to the pink dashed curve. So something that they calculated here. And then you can see that here it intersects at about 3.2 GPa. It intersects the mantle adiabat, I think. And then you have the melt generated. And then as you go to lower temperature and generate more melt, that's the melt fractions. I think that's the accumulated melt fractions that they're talking about here. So that's in this situation, I think in A, situation A. And so for situation B, for batch melting, you can look at that. Then it's just one-time game. You say, okay, let it melt at, I don't know, 2.2 GPa, and then you are going to generate maybe 15% melt. So that's how it goes. And for figure E, then they have the batch melting and the near fractional isobaric melting. So they fix the temperature pressure, and then you can look at how the melting occurs. Of course, the melting has a very high melt fraction, but the melt that generated, as melt generated by 0.4 weight percent, then they pull them away. So that's how, I think that's how they're doing that. And then here you can look at that for each temperature and pressure, you have a corresponding melt composition that you can calculate it, and the corresponding residual solid composition you can get. And the melt composition is what people want to see as the basaltic composition. But before getting into that, they create a thermobarometer. Here have the pressure and temperature according to the composition of the melt. And then that's the prediction versus the experimental measurement. Here in this equation, it looks pretty good. R squared is really high. So I think that's likely due to the, I say, the relatively simple system as they are presented here. But we can going back to talk about it later on. So that's how they're presented here. But then they are showing this figure is basically what they're showing the results of different experimental results. So that's the modeling. So just now we talked about MAGMARS modeling, and then they look at experimental ones. So they really created some experimental data. And then what they are trying to say is that they aggregate melt, which is the polybaric, near fractional polybaric ones, are the best. So you look at those ones, you will see that they evolve slightly differently. And I don't think there's one that's perfect. There's always some ones that are good, some ones that are really bad, depending on how you're looking at them. But they try to say that aggregated melt here is the best fit compared with, let's say, other methods. And I think that's the information that they're trying to get. But do remember, all the symbols here are experimental results. So people created in the laboratory. And then similarly, they're trying to comparing with other modeling software, such as PMELS, which they attack that by saying PMELS that used for is more suitable for lower FeO content samples such as the Earth, and for the Mars, it's probably going off. As you can see, the experimental results that compare with the PMELS that using those dashed curves doesn't really follow very well. And for the solid curves, they fit better with the results, experimental results. So they're trying to say that. But the reason for that, I think, is mainly because of database. PMELS depends on previous experimental database. And for MAGMARS, they consider a lot of the high FeO content samples that they have been doing. So finally, let's go to look at the Andy-Rondak basalts. So here, that's what they are, as a source composition, the gas, the source composition would likely be. And then you have the P is the primitive peridotite, and the D is a depleted peridotite. It's somewhat similar with what we are showing, let's say what we are expecting that's likely to be. I mean, there's always not a perfect number for that, but you can also pay attention to that Mg number is low. So it's about 75%. That's 75 or 75%. compared with Earth is about 90%, something close to that. And then they look at the melt composition. That's what people try to argue. So you have the P melt, that means the primitive mantle melt that created by the near fractional polybaric modeling, likely the real situation should be. And you look at that and the depleted melt, you see, well, they're getting pretty close. I think here they are trying to see by the potassium as well as sodium. So Na and K. So Na2O and K2O. So that's what they're trying to say. But I don't think that's a very big difference. But they're trying to say these ratios are really matched. So, but to me, it looks like they're all matches. Of course, you could see the melt fractions are very different. So primitive melt, it needs 22% melting to generate the basalt. Agree with the result. But if you look at the depleted melt, you just need a very small amount of melting to reach that. Actually, the depleted melt should be harder to melt. But of course, they're putting a different temperature pressure for that, for it. So there then, that's some of the, I think, arc waving ones, because you do have different ways of doing that, because you have different compositions, you let them go in different melting, and you can reach the same, very similar composition. And some of the other controversies here is that even the primary basalt composition under your deck is still controversial, because those basalt are not just basalt. There are the basalts that with the crystallization of olivines or other minerals. So people always debate about it. Even on the Earth, it's less controversial on the Earth because we have a lot of samples. We do have the abyssal peridotite. We have other metals and like this, so then you have better way of knowing how the trend goes. But for Mars, it's pretty hard because there's no peridotite so far as we know. Okay, I think that's so much about it. Okay, I think let's discuss about it. OK， 大家有什么问题吗？有什么问题吗？或者有什么 comment， 或者有什么疑惑？
这个只能算 A， 就只能算 Mars。
我觉得也不是，照说的话，它应该是个扩展的数据集，你可以这样理解。如果说 P mouse， 比方说它 FeO， 其实 FeO 也有高的 P mouse， 只不过不够多，它弄了更多上去。但在我看来，这套东西就是，如果你应该放更多数据集，应该就是能 cover 更广的范围。就照说这个 MAGMARS， 如果把这所有的前面实验都放进去，
它就是
既能算地球，能算
一个 specific 它是专门设计来算 Mars。我看它文章里是这么描述。
我认为它的 highlight 是 Mars， 照说应该也能算吧。这套工具在我看来只是数据集的概念，本质上没有什么。
所以还是 NFI 那个模型表现最好。
他认为跟实验的结果对的最好。NFI 还是那个 NFP 那个。NFP 应该都是 aggregate melt， 是不是？我理解是这个。
aggregation 的话它就是容易点出来，然后它再重新再算一下那个原来剩多少，再剩多少，然后把平均的成分、容体成分再算。
对，把对，
就是再算个平均成分。
照说那个 temperature 也是变的，当然那个 polybaric 可能是这个。
是不是在同样的压力下算
？polybaric 不是
，polybaric
最后一个是
等压的，
最后一个是等压的。
对，所以他觉得等压跟变压没有什么太大区别。
那可能压强就对它的 melting 影响不大的，在它的体积里。
但是每一步的话，如果温度很大变。温度
对你的温度变化序列里面，就是说，如果要考虑到就是你在微量元素的东西，
容易程度变，但是就温度和容易程度有变，然后压力变。
那个是 isobaric 肯定是压力会变。
对，
嗯
就是 OK，
polybaric 是都变的。那 polybaric 它是我理解是它 polybaric 它是从3.2个 GPa 开始算起，
对，
然后我不知道它是以多少的 increment，它用的那个我逐渐的从下往上走，应该就是
这个应该是经典的那个分流容的模型。
是
经典分流容就容易点数学那个压力，
是
就是它是积分那个，
是更接近于。
然后那个是相当于最后一个是 P 质容的一个变体，对吧？P 质容也是相当于是容一次嘛，容一次出来平衡之后，然后也是它那个圆序，你看画那个圈也是跟地曼在那个地方平衡，但是它的不一样的地方，它是在压力相同的情况下，它融了很多次。
你说是 C 还是 D？
就是 C 跟就是那个
C
对，就实际上最后一个
B 我理解是只有一次，
对，一次平衡就融多少都出来了，是最简单的模型。然后后面那个相当于是 Martian Mantle 的变体，相当于是
没错，
对吧？
没错。
这个跟高理工那个想法，
我用这个
本身其实 Martian Mantle 在最早的那个公式里，它跟压强根本没有关系。只是说后续比如说像这个模型，我记得97年的时候就有人在研究猫这种提出来，就是一边往上走，交叉互相线之后这种线，
这是复杂一点。
对，然后之后就有人做简化的，这就是两种不同的情况。
因为在我看来，这个就是你的 polybaric，就是那个压强估计影响不是很大的原因，是因为你看图 A、B、C、D，图 D 里面那个 solidus 和就是 solid 这个 slope 好像没怎么变，你这看，是吧？这 solid 都快变成也不是快成一条直线了，也差不多了吧？所以它这个变了之后。是不是影响并不是很大？也不是，它和那个物象线不和 mantle adiabat 和实际的温度的变化还是比较大，还是有差距的，所以它压强越低，应该是融的程度越高，对吧？
对他们做模拟是，就是因为实际情况肯定是变，就是实际情况很复杂，一直是变。然后你要简化模型，就是固定一个参数之后，它自由度降低之后，你可以去算更简化的。
其实这像火星、月球啊，你就把它当做另外一个克拉滕或者另外一个莫尔布，就是它是地球里面比方有十几个克拉滕，再多了一个那个火星，那 data 值不是太多而已。
那它这个像那种 initial melting，不知道它那个 model 有没有提，就是它初始熔的
成分，
初始熔那个温度，它是从什么时候开始增加？
它应该是从 mantle adiabat 开始。
对，他说好像是降到0.1%的多天之后开始的。但是有一个问题就是，它没有一个，
你这怎么确定？
对，它没有一个预先确定的这个 solidus y。
所以我理解是，如果是那样，就有的地方应该就不容易。所以他算的，比如我猜他是不是从5个 GPa 开始算起的？那5个 GPa 算起，他假设这个是0.1个那个 weight% 的容体，然后剩下的 solid 是多少？然后发现，哎，这个 solid 是比你现在体系的那个温度还高，那咱就不融了，然后再就往上面再走。比方说再看4.8个 GPa、4.7个 GPa，
它这个是不是跟它实验相结合？因为实验它是能看到，就是不同 GPa 的它那个容体。
但不实验你做不了这么多东西，
就实验了某一个嘛，就可能会恒定某一个 GPa，然后看到有没有问题，它是不会结合实验。
它是这样，就是它通过实验来去那个改进这套模型里面的参数，
对，
然后再拿这个东西，然后再去算。
对，
所以在我看来，你可以认为两者之间没有直接的关系，那个有原理上的关系，但是并不完全那个对应。当然你说这个他去看他3个 GPa 的实验，3个 GPa，比方说1450度的实验，看里面有没有 melt， 也可以回去翻看他这篇文章里写这样的实验里面有没有存在问题。
这个模型太 tricky 了，这个东西就是你说实话，就是你设定什么样的参数，你就能得出什么样的结果，可以变。因为之前我跟陈阳的研究，他们那个高领，那个参数就随便调。
有什么样的参数？
就是比如说 initial temperature，他们就是
就比如说现在我一个橄榄油，我想让它融，然后如果按照就是说前人给的图像线，我估计它应该是在1200摄氏度， 但是在他们的模型设定里面，我强行让它在1350摄度，这样就是说就非常的武断的一个判断，但他们就这么做下去。
但他这个比如说稍微好一点，不就是他认为互相线是跟 composition dependent，就你剩下的 composition 是多少，我再算出一个 temperature，不是我，就是它的 solid 不是随便赋的一个值。
对。
但是那个 adiabatic， 当然 adiabatic 你可以稍微弄高点，弄高点弄低点也可以，但是不能太离谱，你总不能把 adiabatic 弄成比方1700度，也不能把 adiabatic 弄成1200度，就是那个 mantle potential temperature。
因为有些玄武岩的那个玄武岩溶体的，它那个温度会有很高的，比如说1600、1700。
我理解应该不会，这1600不都应该是喷发体验那个？我理解这样，就是如果说以我们所知的地球和火星，你弄到这么高的温度，然后弄出来那个岩石，它就不是玄武，它就一定是超级星。但当然，除非说你人气又出现很多很极端的东西啊，那是另外一回事。就我们理解这个感染岩体系，你要融来融去，融出来的东西，应该就不是我们见到的这个。地球上生物岩不是8%到15%嘛？这个上面按它这个做的，有不同的 Peridotite，那6%到8%，也大差不差。但我认为这个工作做完就仿佛又没用，因为你看弄了半天的不 solid temperature 不还是1400摄氏度左右，然后你各个成分都有可能，对吧？这可能这主要因素就解决不了这个问题，你没办法，你也只能等着什么时候那个火星回样。但火星之前美国的2024计划又退了，2080年能回来就不错了。这是你有的，成为送那些都测不了，无量元素也测不了。这有些东西跟微量元素可能更敏感，这主要的是太容易资源起落。再说好像那最后那结果里面，我看就是
它那个模型是改进的晶体，它加了磷在里面，对吧？我看
磷元素，
它是加了，
但我认为没什么用。
哎，
我个人认为没什么用。那个，当然你多出点数据，大家感觉欢迎。但估计没什么。
所以它还是用基本上是用李斯晶体那种模型来算原始值，就相当于原始800嘛，对吧？
对。或者说大家经常说的这个，包括 p-melts， 就是这些，就是办法是老办法，数据稍微加了一点新数据。再说可能就算那个 melt 的那个 solid 的地方，可能稍微他做了一些改进，小的改进。但我认为这个结论不是还是1400摄氏度左右，人家 p-melt 上算是比这高点，什么1480度，
啊，小100度。
啊，
好小，稍微差100度
，1400、1300度，
有1500、1400，
对吧？但1500、1400也取决于你用啥成分在这种。对，人家那个拿批量算出来，拿批量拿什么东西开始？在我看来，1500、1400也差不多。这个其他的误差都够大，因为底下你也不知道有什么。那我也有点怀疑，它有的参数它会试了好多遍模型。我认为它就真的是你能得出那个什么 p melt、d melt 这种算出来，刚好你的 FeO 就是这么多。
他们俩都是没有什么影响，差不多。
对，我觉得大多数基本都没什么，
就是在不同的那个 melt 这个 fraction 情况下，它们成分一样，熔比例不一样，
对，
比例不一样。
因为我之前想，你这样，如果这个 p melt 就是 primitive 的 composition，如果它只溶一点，比方它只溶个，比方说6%的部分熔，它那一定是里面会非常富铝。比如说啊，可能铁也会更富铁一些，就是不相容的都跑出去了，是吧？那我再多溶点，溶了22%，跟你又稀释下去了，把你的铝，比方说是本来说6%的 p melt 6%的时候熔的时候，那个铝是15%，然后你给你溶到22，又给你弄下来，对吧？你这个不相容都倾向于跑了嘛，剩下的跟越来越少呗，又跟 dilute 嘛， 然后那 depleted 的时候，我刚开始就没这么多铝，所以你让我少熔点，只熔6%，差不多跟你这个结果就对上了。但我都有点怀疑，它这个就真的能算的这两个东西就完全一样，就要试过多少次，它到底是调了哪些关键的参数？调了之后是它这两个刚好一样。
模型的话，只展示最后那好了，其他全都不展示。
只展示最后能解释。
解释也不好啊，在最后他拿那个钾钠比去解释，我觉得有点牵强，有点牵强。钾钠比也没差太多，有点牵强。磷呢做了半天，最后磷又不解释了。
是啊，
火星地幔的氧密度非常好。
其实现在又搞不清楚了，因为我以前理解的就是它氧密度是这样算的，你可以想想，就行星它的氧密度，你可以认为如果地核里面的核里的成分都差不多的话，对吧？那你就看那个幔里面有多少 FeO 嘛？比如说极其还原，那就是说，这假设最极端的还原情况下，那些铁都不愿意跟那些氧去bond，那所有的铁都跑到地核里面去，那地幔应该的 FeO 可能就是0%或者极低。是吧？那你氧密度越高，那就证明说我的铁跟氧结合能越强，那我就多点去当到地幔里去。那显然，如果这么看的话，那火星的氧密度应该肯定是最高的位置，117位，是吧？月球和地球应该在中间，然后那个水星是最低的 ，Mercury 是现在认为只有3%的 FeO，所以这是 first order 之外。但是你再仔细去看到每一个地方，我理解是你 really depends，因为到每一个地方的时候都取决于它的 temperature。它熔的那个条件不一样，它不是那个就不一样，并且你每一个熔的园区的里面又不是单质铁这种情况，它都是以某一个 FeO 开始对吧熔到下那个东西出来，所以说这个每到一个地方我认为都很 tricky， 所以我看他们算出了这些就是地球上的可能我们了解比较清楚一点，我们地幔是 FMQ 到 FMQ 减4，大概是这个方面，然后。火星上照说应该是要更氧化一些，要那个火星地，但是我看到的像月球的地幔的话，照说应该跟地球差不多，但是月球的好像也挺还原，就比在属于地球非常还原这个，所以 it really depends， 因为你算不同的园区应该得出的值是不一样，而火星和月球没有 Peridotite， 无论是一个很大的硬伤，很大的硬伤，这地球真的是还是能说得很清楚，地方事儿我们可能认为地的。样品还也不是说想要那样。
问一个非常tricky的问题吗？
你应该多问几个。
就刚才那3个图，就看那 NF。
有这个，你这3张 ABC 是吧？它算那个它演绎了3种可能的情况，
演绎了3种嘛，对吧？
产生的情况，
肯定不止这3种，还有其他更复杂的。
区，就那个地层后面变了。
你可以看到那个就是彩色的那个棒它在变，比如说这个模型它对应变压，就是说我的这个绝热进度线和不上线交叉之后，理论模型上就该开始，然后从熔程度低，然后到熔程度高，它逐渐就我温度也降低，压强也变化，然后随着它就累积的熔体的量就状态就在变。然后这个方框呢，就是指的这个 batch mantle， 就是我直接给定它一个温度压强，然后它在这个状态下就一次性熔完。然后这个呢，就是相当于我每次我压强不变，我温度逐渐升温2个月。
那你今天画的这3个图区别
？3个图的区别就相当于你可以理解成，就是说这个我的园区它就可以包含这么大一个压强范围，然后就相当于我从低压就不断就汇在一起，就像沙丁鱼一样，一直汇到最后。
这么深的地幔有，讲说地幔，一般不说岩浆园区在
对，
中间就
然后这个是对，它就直接在这儿，
就是相当于
没有，
它
就相当于这就直接是一个鱼群，
就如果也是 就是如果
那第三个的话，第三个
像
就是说
Prof.Zhang
它是一种介于两
那你要下地慢的
假设，
会融体，
就是我假设我所有的东西都
下面一个压
对
对，下面的
对，
也有可能，因为比方说夏令曼他认为夏令曼里面，比方说FeO content 然后它的效率很低，就是是比较奇怪的啊，而不是我们认为的 BSE。
那很灵活，就是说我模拟不同的过程，然后从不同的容体组分之后，
那些地慢做这个，然后一般都不就湖南那些来的这个
不是数据是
热黑
它采的模型匹配的地址，
在我理解它是 P，它上的是 P，首先是 P，首先是 P，第二个是 max，
再选
对，
最后能否产生这样的水平，就是
在直播
策略。P 首先是 P 的是今天都在产生，因为不停的它是一个 P 的意识。这还真有这个比较。那个会这样打比方吧，比方说你那个吃了什么东西吃了能够那个让它产生汁水，结果分享吃了，
吃了刚跟加分一点，
没关系，那你们吃的跟他弄个吃的例子看地方也一样，也不是跟他所有人都一样，你吃了，你在家
就假设你现在吃雪糕，
雪糕不行，温度太低，你就弄个什么高一点，就是你蒸一个什么，或者是你蒸啥，蒸啥，
报菜名是吧？
报菜名，
蒸什么样？
蒸出来要有汁水的东西。
蒸出来要有汁水。
相当于地球那个岩浆相当于是熔的地底下的成分，然后熔地底下那些固体成分变成那些
蒸啥都会有水，熬出油气呀！
这个是你不理解的，
熬出油，哪个
不同的情况下，
你不理解
什么样的过程？
不理解。那个红色的知道是什么吗？
他刚讲了，我知道，好像是岩浆。
对，红色就是岩浆，高温相对比较高温的。然后，
就是边走边融嘛。
嗯。
第二个就是倒奶的。为什么会这样？就是他讲，
这是模型嘛，就大家在想象，因为大家
对。
没有办法。
为什么岩浆会是这样？他要做这三种假设，他这三种假设的来源
是来源于前期大家很多工作积累，就是第一个非常今年上个世纪，然后最早期做那种这样的园区。
那他们算这种
或者这个指定这些园区还是怎么
因为比方说最早大家认为像这个固象线，就温度在固象线之上就产生熔体。那个。大家也通过这个可以解释为什么比方这100公里的地方可以看到一些异常的，是吧？就是那地球仪在往上热天残，后来大家甚至又在300公里的地方又是他说这个骚人怎么都不可能产出来，后来我小时候做实验说我在里面加点碳进去，然后那个碳的那个骚人就刚好和这个曼特个是在10个级别中小创作，所以说一就你在这说这个300公里。那个大洋底下300公里经济程度是
那是因为有碳。
对，有碳来说。
但这个模型最近是地球化一下，就是这个就是
这两种间都是
地球化一种，就是大家都解释，就地球上有那么多岩浆，它岩浆的源是在哪？怎么情况？它为什么在这个有一些基本里面那个物理化学，就它下面 PT 就是上顶，就相当于在特定的温度和压力下会产生特定的那些矿物质和会产生一些
岩浆和溶体是一个
是一个在这里面是
在这里是一个
岩浆可以让是归正不停的变，它这个拉有的一次性它们每一个
就是我们这里的地球体下去，当然也是其中的两它们碳水也是挺低，但很少。
然后我想你可以这样理解，就是那个有点像那个，比方说蒸馏酒那样多，你弄个后盖，然后一蒸馏，然后底下的那个你把一桶的酒的话，不是有酒蒸气，是吧？你可以有一个办法，就是一直那种概念，一直堆盖，然后等蒸馏蒸了很久，然后一桶咔嚓盖子一揭完，蒸汽上收在下面，是吧？这是一种。第二种的话，可以让慢慢加温，加温再吸，只要一层一点小气在这个地方接着。 然后再乘以9再减，那事实上你每分流出来的这些9基本上都是4对吧？那相当于有2种极端情况，第一种就是盖的过盖的这个 close system， 所有的都没有打爆，然后你们达到平衡，咔嚓最后一节过7个的这个气质。第二种情况就是 open system， 相当于我产生1.7我的3分倍，所以也正9万，但你每次接的成分不一样，但是你接了很多次，最后也会但是我刚才说的，这个 situation 1和 situation 2，得到那个最后你拿那个9成率数是不一样，不一样。对吧？
对，跟你游玩就一样了。
啊，你赶紧把这游玩是一样的，就你们酒都没了，是一样的。对。
但是它那3个就跟地球，
对，地球。
那地球能
一样。他俩就很像，
就是我现在地球都是岩石构成，而不是地球飞过。
或者说你认为地幔流过那些或者会是月球温度高，月球差不多，就是应该还有其他的那个热是非常不太具体的成分不太一样，但是晶体主要是不变。你是你学机学矿物就学过，超出那个，但到了木星就。
木星97，
就那些就对，他们有气体加4的，所以它里面固体那些东西可能是以钢冰的形式，对，完全不一样。但是它没有什么，它肯定也有的，它没有几克啊，就是那个它主体容易低是完全。所以到了 TD 平台上面导一个什么数据会变成形态学，也很正常，不要奇怪。因为成分差不多，这个是
我可能要跟那边合作。
TD 要合作，明年就可以包装，可以包装，
他们平